Right, we've got a worked example in the coordinate systems section of the further maths syllabus here, the Edexcel further maths, to do with a rectangular hyperbola. As I mentioned before, this is kind of coordinate geometry, but sort of industrial strength coordinate geometry, really. This question is actually from the student book. Let's have a look. A rectangular hyperbola H has Cartesian equation x xy equals c squared, c greater than 0, and the point ct, c over t. It's the general point. It's also the sort of the parametric equation of the curve, isn't it? Is a general point on H. Show that an equation of the tangent to H at that is x plus t squared y equals 2ct. Okay, so all right, so we want the equation of the tangent, so we want the gradient of the tangent, don't we? So we can find that by differentiating the equation of the curve. So if we find the derivative with respect to x of this equation, then we're going to differentiate implicitly and get this out of that. And that's going to give us a derivative of minus y over x. That's the gradient of the tangent. Incidentally, we can find the gradient in terms of t as well, and so it's kind of tempting to use that. But as you see, really, this is kind of more about this problem is more about sort of Cartesian versions of lines. So we need to go down that route. It's not altogether obvious, but that's what we're doing. So the equation of the tangent is this, and so there's our gradient in there. It kind of looks wrong, doesn't it, with this sort of cancellation going on with the x? But anyway, plus the intercept there, which I've used k because obviously c is used in the this equation for the hyperbola up here. So that gives us k equals 2y. And then, so if we kind of then plug that back in there and we use the general point here in our gradient, all right, so this is minus y over x. Okay, that's c t there. That's not very clear, but that's a ct, and then this is 2y from there. Okay, so that's going to give us this, which then gives us that, which is the required result. Okay, so then it goes on to say the point P lies on H. Okay, yeah, that's here in the diagram here. P lies on H. The tangent to H at P cuts the x-axis at the point X there with coordinates 2a 0. So that's 2a, x is 2a along the x-axis. Use the answer to part A, yeah, this, to show that P has coordinates of that. Right, so okay, so that's the equation of the tangent, or px as it's drawn here. And then if we just substitute in there the coordinates of x, then we're actually going to see that t is equal to a over c. And then we can put that back into our general point there to give us the coordinates of P. Okay, that's part B. The point, sorry, this is point Q. P has that P as point B there. Right, beg your pardon. Right, then we go and say part C, the point Q, which lies on H, has x coordinate 2a. Right, so that's all right. So that's vertically above x, isn't it, as it were? So find the y coordinate of Q. So that's probably the easiest bit. So all we need to do is substitute in the equation of the curve the value for x, which is 2a, and that's going to give us y equals c squared over 2a. So we know the x and y coordinates now of that point Q. D, hence find the equation of the line OQ where O is the origin. Right, so so we've worked out what Q is. So OQ, this is the line from the origin to Q. The gradient of OQ is going to be the rise over the run, which is that. And the equation of OQ is going to be this. There's no intercept, obviously, because the line goes through the origin. So that is the equation of OQ. Right. Next. So we're now going down to part E. Find in terms of A, the lines OQ and XP meet at R. Find in terms of A, the X coordinate of R. In terms of A, the X coordinate of R. Okay, so we've got the equation of OX. If we got the equation, equation of O, that should say OQ, of course. Just change that. Okay. So we know that. So if we know the equation of PX, then we can actually find the intersection. We don't know that yet, but we do know that P is this point here. And X is this point that was given to us. So the gradient's going to be the rise over the run as we go from X to P. So that is the rise, that's the run. That gives us that. So that is the gradient of Px. And then we can use our little formula here with the gradient here. And using point X there. And when we just simplify that, we're going to get this. So we now got the equation of Px there, and we'd already got the equation of OQ from there. So R is at the intersection of those, so all we need to do is eliminate Y, and we form this equation of the intersection. Right, bit of reorganization to there and there, and finally that's going to yield that X is going to be equal to 8a by 5. Squares cancel out there quite nicely. So that's the X coordinate. Right, so now we want, that was part E, so we're going to part F. Given that the line OQ is perpendicular to the line XP, which it doesn't look like in the diagram, does it? But if we drew it correctly or drew it with the right parameters, then it would do. Show that C squared equals 2A squared. All right, so that's F. All right, well, we know the gradients of, well, we know the equations of these, and we certainly know the gradients of them. So now we know they're perpendicular. If we multiply them together, we're going to get -1. And the equation that comes out of that is going to simplify to C squared equals 2A squared. Yeah, which is what, back up here, we're being asked. And then finally, find in terms of A, the Y coordinate of R. Okay, so wind back down again. So R is on this line. Yep, there it is, on this line, which is OQ. And we know the X coordinate because we worked that out there, 8a by 5. So basically we can substitute that in for our X there to give us this. Now we've still got C squared in there, but we do have a relationship between C and A, which we worked out over here in part F. And so if we substitute that in there, we've got no C's left, and there's a nice bit of cancellation goes on. So that's going to give us the Y coordinate is 4a by 5. So that point R is at 8a by 5, 4a by 5. Okay, and we've got to the end. Kind of rather tricky problem. It's a bit messy, to be honest. Lots of working out, lots of constants and so on. Um, I think perhaps one of the most difficult things is just actually um, convincing yourself that you need to take the Cartesian form of the of of the gradient in order to progress. Which to me wasn't completely obvious. I was tempted to use the parametric form, but the problem is mostly about sort of Cartesian equa forms of equations. So probably uh, would give a clue if one was to start doing it from scratch. Anyway, so I hope that has been useful. If you've got any comments or anything wasn't clear, just mention that in the comment section, and I can address it. Maybe redo the video and whatever. So anyway, thank you for listening.